So in these next few slides, we're going to use the example of sulfur dioxide, SO2, to illustrate this concept called resonance for Lewis dot structures. So, but first, let's write the Lewis dot structure for SO2 first. So to write the Lewis dot structure for sulfur dioxide, do the same steps that we did in the previous video with regards to molecules. You first figure out how many valence electrons this molecule has by summing the valences for the individual atoms. Both sulfur and oxygen are in group 6, so they each contribute 6 valence electrons to give me a total of 18 valence electrons for my structure. I start my Lewis dot structure by writing down my central atom, my first atom, first as a center atom, scattering my outer atoms around it. Then I start making single bonds between my center atom and my outer atom. In this case, remembering that a single bond is 2 electrons. In this cartoon, I've just chosen to show the single bond is 2 electrons, but you could have easily just drawn a line between the sulfur and oxygen. But doing that, you have now used 4 of your 18 valence electrons. The next step is to complete the octets on the outer atoms, so those 2 outer oxygens. Doing that, each oxygen now has a total of 8 valence electrons. Remember again that the electrons that are shared between 2 atoms in between the shared space count for both. So the oxygen on the left and the oxygen on the right, they both have 2, 4, 6, 8 valence electrons. So when doing that, I have now used a total of 16 of my 18 valence electrons that I need to use for my Lewis dot structure. So any extra electrons you have after completing the octets on the outer atoms always go on the center atom. So I've put that 17th and 18th valence electron here on sulfur. So we are done placing our valence electrons. We have used 18 out of 18. But hopefully you can notice that my sulfur atom, my central atom, is not happy with regards to the octet rule. My central sulfur atom only has 1, 2, 3, 4, 5, 6 electrons, and it wants 8. Can't just add another 2 electrons to the center atom. What happens is you need to look at the 2 atoms attached to it and see if either of those atoms have lone pairs of electrons that can be easily shared between the oxygen and the sulfur. And in this case, there are lone pairs available, and actually there are lone pairs on this oxygen on the left that can be shared. And there's a lone pair on this oxygen on the right that could be shared. So we could potentially have a lone pair from the oxygen over on the left being shared to give you a Lewis dot structure similar to what's here. Or you could just as easily see a lone pair from an oxygen on the right sharing a lone pair of electrons. We only need 1 double bond to form because sulfur just needs 2 more electrons to have the octet. So both of these Lewis dot structures that are at the bottom here, both of them satisfy the octet rule because all of the atoms have an octet. We've used all the appropriate electrons for Lewis dot structure. So which one is correct? Which one would get you the maximum amount of points on the exam? Well, the answer is that they're both correct. And that's where this concept of resonance comes into play. So resonance, in chemistry terms, is just a fancy way to say that there is more than one equivalent Lewis dot structure that can be written. Now, you talk a lot more about resonance structures in Chem 1. So obviously we're not going to talk that much about them. On the exam, I'm not going to ask you to draw all possible resonance structures for a molecule if they even exist. Okay. I'm just more concerned that you know about this concept of resonance structures, which is that for some molecules, you can draw Lewis dot structures that follow all the rules and are still valid. And like I said, there are some caveats to that. There are some resonance structures that can be better than others. You talk about that more in Chem 1. We're not going to talk about them here. I just want you to know, for intro, I just want you to know the definition of resonance structures, what that means, and know that resonance structures can be possible primarily for atoms or for molecules that have oxygen as an outer atom, or specifically lone pairs that can be shared with a central atom. Okay? And that's really all I'm going to say about resonance structures. I know it was mentioned in the worksheet and it may be mentioned in the Lewis dot structure lab, but I'm not going to really focus on that concept. So the short answer is which structure is correct, which Lewis dot structure is correct for SO2. Both of them I would give you credit for because both of them follow the rules and satisfy the octet rule. So last bit of information about Lewis dot structures for this video. Especially if you go on in chemistry, you will find that there are quite a few octet rule examples that are exceptions to our rules. There are some molecules that have a central atom with less than an octet. There are some molecules that have a central atom that contain an expanded octet. So for example, in this molecule, in this Lewis dot structure, sulfur, my sulfur has 2, 4, 6, 8, 10, 12 valence electrons. So it is definitely above the 8. But that's okay. Why that's okay, you talk about in other classes. What I want you to be familiar with and comfortable with is using the rules that we have talked about in the previous video for drawing Lewis dot structures. And also remembering that once you draw the Lewis dot structure, any extra electrons go on the central atom after forming the octet on the outer atoms. So let's finish this little vignette with an example of a Lewis dot structure that does not follow the octet rule, but you will still get the correct answer by following all of the rules that we have talked about. So let's say I was to ask you for the Lewis dot structure for SbF5. You would go about doing the Lewis dot structure exactly the same way as we've done the previous ones. First things first, figure out the number of valence electrons. Sb antimony, it's in group 5. It contributes 5 valence electrons. Fluorine is in group 7. There's 5 of them. So they contribute 35 to get a total of 40 valence electrons for my structure. I start by putting my first atom as the central atom. Scatter my outer atoms around it. I've got 5 fluorines, so I've scattered 5 fluorines around. Now I'm going to start placing my valence electrons by first doing single bonds from my center atom to my outer atom. Remembering that single bonds again are 2 electrons. So I'm going to count by 2s. 2, 4, 6, 8, 10. So I have now used 10 of my 40 valence electrons. Next thing, I need to complete the octets on my outer atoms, specifically the fluorines. Remembering octet 8 is 8 electrons. So when I put my octets, when I start doing my electrons, I kind of count by singles. Okay, so I've already used 10 of my 40. I'm going to start doing my octets. So 11, 12, 13, 14, 15, 16. I have now used 16 of my 40 valence electrons. This fluorine is happy now with an octet. It has 2, 4, 6, 8 electrons. So I can move on to the next fluorine. So 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Try and make these a little darker. So I have used all 40 of my 40 valence electrons. Each fluorine has an octet. This fluorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Same for these other fluorines. So I've used all 40 of my valence electrons, but SB, antimony, has 2, 4, 6, 8, 10 electrons in its outer shell. But that's okay. That is okay. We still needed to go ahead and use all of the 40 we were given. So this is indeed a correct Lewis dot structure for SBF5. My whole point in showing this example is to show you that there are exceptions to the octet rule. There are some central atoms that have expanded octets. If you get a problem like that, particularly if it uses a non-metal as the center that's further down the periodic table, don't worry about it. Just go ahead and draw the Lewis dot structure using the rules that we've talked about, and you should get the correct answer.